So I just finished lecturing on non-singular matrices. The major takeaway there is this concept of a matrix having an inverse. What that means is that if your matrix has an inverse, that the inverse is another matrix you can multiply on both sides to get the identity matrix. And the concept of being invertible, so the concept of having an inverse, is the same thing as the concept of being non-singular, meaning that your matrix is square with full rank. Another thing we did in that lecture was we calculated inverses. And the way we did this was by augmenting the matrix we're studying with the identity matrix and then doing row reductions. I've written some Sage code here that will do that for you. So if you want to augment your matrix with the identity matrix, remember that there's syntax to do this. The identity matrix is built into Sage with the syntax identity underscore matrix. And there's also syntax for augmentation. So what you do is you define your matrix A, and then you write dot augment open parentheses. Then you input the appropriately sized identity matrix, and the appropriately sized identity matrix would have the same number of rows that A does. So here I write identity underscore matrix, open parentheses, A dot in rows, open close parentheses, so that the identity matrix has the right size here. And then I also like to see that subdivision. I like to see that line, so I write subdivide equals true. So in my code here, all I need is one line where I define my matrix. And then there's two print statements. The first print statement will spit out the matrix that I put in augmented with the identity, so I can make sure that I input my data correctly. And then the second print statement will print out the reduced row echelon form of that augmentation. And that will tell me whether or not the matrix is invertible. I can check whether or not the matrix is invertible by verifying that I get the identity on the left. And if I am invertible, so if I do get the identity on the left, the matrix that pops out on the right is the inverse. So let's click evaluate and see how this goes. So here I get the matrix I put in was a 3x3 matrix. And when I augment with the identity, of course, I get my augmented matrix. And then now, Sage went ahead and did the row reductions for me and found that the reduced row echelon form of my matrix with the identity augmented on it produces the identity on the left. So that tells me my original A was actually invertible. And so the matrix that pops out on the right here is the inverse of my original A. So my 3x3 that I started with has its 3x3 inverse here. Let's see here. So I do want to point out, maybe I can change one thing in this matrix and give you something that's not invertible. So note here, the second column of A is 2, 1, 1, and the third column is -1, -1, -1. Let's say that I make the first column 1, 1, 1, so that the second column is really the negative of the third. That means that I can't have rank 3 because the third column is related to the second column. So I'm going to put a 1 in that 1, 2 entry, and let's see how that changes this example. So now the example changes. My matrix A no longer is 3x3 with rank 3, it's 3x3 with rank 2. So I do not get the identity after row reducing when tacking on the identity matrix. So that means that this matrix is not invertible. So that's a nice example, I think. Now, of course, the algorithm that we're doing here, you could just maybe ask for the inverse, and Sage has that capability. So if you just don't want to go through that trouble, you could just say, okay, well, what is the inverse? The syntax there is A dot inverse. So here, all you have to input is your matrix and call it A. The two print statements will tell you what matrix you input, and then the second print statement will tell you what the inverse is, should it exist. So let's click evaluate here and see what I put in. So here, I have the same matrix that I started with in that previous example. It's my 3x3. And you'll see that A inverse really is equal to the matrix that popped out after we did our augmentation before. Let's double check that. So let's put back in the default here and evaluate. So yeah, we see that the inverse after we did the augmentation method had column 0, 1, 1, and so 0, 1, 1, 1/3, 0, 1/3, 1/3, 0, 1/3, and then -1/3, negative 1 is that negative 7 over 3, and negative 1/3, negative 1, negative 7 over 3. So we do get the right thing here. What's interesting is if you played the same game that I played before, so if you change this 2 to a 1, again, that will take me from a rank 3, 3x3 to a rank 2, 3x3. And if I click evaluate, you'll see that the code throws an error because the matrix that I input here is no longer non-singular. And you'll even see it's built into the system. In order for the matrix to have an inverse, the matrix must be non-singular. So we're learning the theory correctly.